Welcome back, class. So now that you've had a chance to watch a couple videos overviewing atomic theory and some of the ideas that go into it, let's talk about some of the concepts a little further. So in this section, we're going to talk about some of the fundamental laws that were discussed that led to the development of atomic theory. So the first one that we want to look at is simply conservation of mass. So this was discovered by Lavoisier, and essentially it states that in a chemical reaction, matter is neither created or destroyed. So in other words, the mass that we start with will be the mass that we end with. That mass may take on a different form, right? We may form different materials at the beginning, a chemical change, as we discussed, but the total mass will be the same. Right? So mass is conserved in a chemical reaction. Now, a couple of other fundamental laws that were discussed were the law of definite proportions and the law of multiple proportions. So let's first look at the law of definite proportions given to us by Proust, which essentially states that compounds always have the same proportion of their constituent elements. So this goes back to some of the ideas that we've mentioned earlier, that, for example, that when we have a particular compound, it always has the same chemical formula, right? So when we have water and it's H2O, for example, that every molecule of that water, or of water, has 2 hydrogens and 1 oxygen. It always has the same formula. Now, as a result of that, we're always going to have the same proportions of those elements in terms of their mass. So let's do a couple examples to sort of illustrate that. So in the first one, if I have a 10-gram sample of calcite molecule that contains 4 grams of calcium, and I want to know how much calcite contains 0.24 grams of calcium. So in other words, how much calcite would I need to have in order for it to contain 0.24 grams of calcium? Well, the first piece of information there gives us the proportions, right? It tells me that in a 10-gram sample of calcite, I have 4 grams of calcium. So that means in every 10 grams, I'm going to have exactly 4 grams of calcium. Now, another way you could think about this would be a percentage, if you will. So what that means, another way of thinking about that is that calcite is 40% calcium. So you could think about it that way as well. But let's think about mathematically how we go about solving these. So we're going to start with our 0.24 grams of calcium. And we're going to use the ratio that it told us, that for every 10 grams of calcite, I have 4 grams of calcium. So we're going to follow the tenets of dimensional analysis, right? So we want our grams of calcium on the bottom to cancel out, right? That's our given. And we want the grams of calcite on top, right? That's our desire. So this will allow my grams of calcium to cancel out. So according to what they told us, we have 4 grams of calcium for every 10 grams of calcite. So if I simply do this math, I end up with 0.60 grams of calcite would be needed in order to contain 0.24 grams of calcium, or 0.24 grams represents 40% of that 0.6 grams. So this is the fundamental idea behind the law of definite proportions. Sometimes you might hear it called the law of constant composition. Right? So let's try one more example. If we have a 26-gram sample of water, it contains 23.1 grams of oxygen. So how much water would I need to have in order to have 40.8 grams of oxygen? So in similar fashion, we start with the sample that we don't know the information about. So in this case, we have 40.8 grams of oxygen in some sample, but we know that in any sample of water, that we have 23.1 grams of oxygen for every 26.0 grams of water. And that's going to hold for any sample of water. They're always going to be this same proportion, right? 23.1 grams out of every 26 grams. And so if I go ahead and do the math here, keeping in mind significant figures, of course, I would get 45.9 grams of water would be needed in order to contain 40.8 grams of oxygen. Again, so if we wanted to establish this as a percentage again, we could, and by using this information, we would see that water is always 88.85% oxygen by mass. So any sample of water is going to follow that percentage. So, law of definite proportions. So now let's turn our attention to the last of our sort of fundamental laws here that we're going to look at, and that's the law of multiple proportions developed by Dalton. And what this says is that when the same two elements form two or more different compounds, for example, carbon monoxide and carbon dioxide are illustrated in the book, the mass of element B, right, that combines with either 1 gram or any fixed amount of element A can be expressed as a ratio of small whole numbers. So let's take NO2 and NO as our sort of example. So we have two elements that are forming two or more compounds, right? So we've got two elements forming two compounds, right? Nitrogen and oxygen forming these two different compounds. So we're going to use nitrogen here as our fixed amount. And so what we're going to do is we're just going to look at these two compounds and just simply, based on the masses on the periodic table, we're going to look at what would the masses be in this compound. So for NO2, let's do it like this. Let me rewrite this a little bit different. So let's do NO2 here. Oops. And so for NO2, I would have 14 grams of nitrogen. And for oxygen, I would have two oxygens. It's 16 each on the periodic table, so 32 grams of oxygen. And for NO, if we do the same thing, I would have one nitrogen, so 14 grams of nitrogen, and one oxygen, or 16 grams of oxygen. So let's apply this idea of multiple proportions. So our fixed amount, right? So A, right? So our A here is nitrogen. So we have a fixed amount of 14 grams of nitrogen. And our element B here, right, is the oxygen. So the masses of B that combine with this fixed masses of A should be able to be expressed as a ratio of small whole numbers. So the way that we go about showing this is that we take whatever our fixed amount is and we divide everything by that fixed amount. So in other words, we're going to divide everything by 14. Right? So if I divide both of these by 14, and of course they are the same, so I get 1 here and 1 here. So as expected, since the fixed amount, there's a 1-to-1 ratio here. Now let's divide both of our masses of oxygen by 14. And if we do this, we get 32 divided by 14. We get 2.29. And if I take 16 divided by 14, I get 1.14. So if we look at the ratios, of course, the ratios of nitrogen are 1 divided by 1 equals 1. And the ratio of the masses of B, if I do that, is 2.29 divided by 1.14. There's 2.01. To one significant figure, though, right, we have 2. So as we can see, the masses, if we look back at our law here, the masses of element B, right, that combine with a fixed amount of element A, nitrogen, can be expressed as a ratio of small whole numbers, in this case 2. Right? So this is a demonstration of the law of multiple proportions, similar to the one in the book where they use carbon dioxide and carbon monoxide. Right. Now, next we're going to look at a little bit more in-depth video about Dalton's atomic theory, and then we're going to come back and talk about Dalton's theory.